the magnetic effect of current. The phenomenon of electricity and the phenomenon of magnetism were discovered long ago, but completely separate from each other. For centuries, no one suspected that these two phenomena were closely intertwined. It was only after humans developed technology to generate large continuous electrical currents using an early and primitive form of chemical battery called a voltaic pile that we chanced upon the intimate and inextricable link between electrical currents and magnetic fields. More than a century ago, a scientist named Hans Ørsted was demonstrating the working of a magnetic compass to his students. By sheer luck, he had left the setup of a previous experiment involving a battery and wires untouched on the same desk. During the demo, Ørsted accidentally switched the current on, and immediately the compass placed close to a wire, which was hitherto pointing north, was now pointing east. To us, this may seem trivial, but to an inquisitive man like Ørsted, this event had all the intellectual force of a hurricane. Convinced that he had misunderstood what had happened, Ørsted promptly called in his colleagues and students to make sure he could replicate the same result again and again. He could. From this happy accident would stem great discoveries that fundamentally changed the way humans understand nature. So let's delve into the relationship of current and magnetism in more detail. Before we see how current is linked to magnetism, let's have a look at permanent magnets with which we are much more familiar. We know that a permanent magnet, regardless of its geometric shape, will have two poles, no more, no less. The strength of the magnet seems to be maximum at the poles, and like poles repel, while unlike poles attract. We can understand why magnets behave this way through some simple experiments. When we bring a magnetic compass near a large bar magnet, we notice that the compass needle is affected. The effect becomes stronger near the poles and closer to the magnet, and vice versa. We cannot see the influence of the magnet directly, only its effect on other magnetic materials. It is more helpful to sprinkle some fine iron filings near the magnet. We notice that these filings immediately arrange themselves into a pattern along distinct lines. Based on these experiments, we can define a new term called the field. What is a field? A field is the specific property of an object, like the force it's exerting on nearby objects, which is spread out in space. We can visualize this field as a collection of invisible lines, and the forces are exerted by the magnet acting along these lines. The strength of the magnet depends on the closeness of these field lines. The more bunched together they are, the stronger the effect of the magnet in that region, and vice versa. We can also understand other properties in the context of field theory. For example, these magnetic field lines like to be as far away from each other as possible. This explains why like poles repel each other. These lines also want to be as short as possible. That is why unlike poles attract each other. The force in these lines seems to travel from the North Pole to the South Pole. This explains the behavior of a magnetic compass in the vicinity of a bar magnet. Having understood the very simplistic definition of a field, let us proceed further.